Welcome to homework.
For this question, we are going to be using this balanced chemical equation for the combustion of methane, and they tell us that the enthalpy for this reaction is equal to negative 890.3 kilojoules per mole. For the first part of this question, they are wanting us to find the mass of methane when a certain amount of heat is evolved in the reaction. So we're looking for the mass of methane, and they would like this in units of kilograms. They tell us that the heat liberated from the reaction is 2.8 times 10 to the 7th kilojoules. So first, to start out this problem, we need to find out how many moles of methane that we have. So moles of our methane. And we know that the moles of our methane will be equal to the amount of heat that was liberated from the reaction divided by our enthalpy of the reaction. So 2.8 times 10 to the 7th kilojoule, and we're going to divide that by 890.3 kilojoules per mole. So when we calculate this out, we'll have 3.14 times 10 to the 4th moles of methane. So now that we have our moles of methane, we can find our mass of methane. So our mass is just going to be our moles, and we're going to times that by the molar mass, so 16.04 grams per mole of methane. So when we calculate this out, we'll have 5,03656 grams of methane. They want this expressed in kilograms, so we're just going to divide this number by 1,000. So it's going to be 503.7 kilograms. So this is the amount of methane that we'll have for the first part of this problem. For the second part of this problem, they're wanting us to find the heat evolved when we have certain conditions with methane. So the volume of methane that we have is 1.65 times 10 to the 4th liters of methane. They tell us that the temperature for this reaction is 18.6 degrees Celsius. I'm just going to turn this into Kelvin by adding 273 Kelvin. So we'll have 291.6 Kelvin. They tell us that the pressure for this reaction is 768 millimeters of mercury. So I'm just going to turn this into atmosphere. So we have 1 atmosphere for every 760 millimeters of mercury. So when we multiply this out, our pressure is going to be 1.01 atmospheres. So we are trying to find heat evolved, so we need to find the moles of methane. So for this, we're going to use PV is equal to nRT. So we're looking for the moles of methane, so PV over RT. So moles of our methane is going to equal our pressure, so 101 atmospheres, times our volume of methane, so 1.65 times 10 to the 4th liters of methane, and divide that by the R value. We're going to be using R is equal to 0.0821 liters atmosphere per mole Kelvin, and then times that by our temperature, which is 296.1 Kelvin. So when we calculate this out, our number of moles is going to be 696.1 moles of methane. So now we can find heat evolved. So heat evolved, and that is going to equal our moles of methane and we're going to times that by negative 890.3 kilojoules that we got from our enthalpy of our reaction. per 1 mole of methane. So our heat evolved is going to be 619.74 times 10 to the third kilojoules. This would be negative, but that would be heat associated. We want heat evolved, so we're just going to take out the negative sign. So this would be the heat evolved for the second part of this problem. For the third part of this problem, they're wanting us to find the volume of water vapor that can be heated when there is a temperature increase. So we're looking for the volume of water vapor, and we're looking for it in units of liters. They tell us that the specific heat of water is equal to 4.186 joules per gram degree Celsius. And they tell us that our temperature, or our delta T, so our final temperature is 60 degrees Celsius, and our beginning temperature, or our initial temperature, is equal to 8.8 degrees Celsius. Alright, so when we calculate this out, it's going to be 51.2 degrees Celsius for our delta T. So our mass of our water is equal to the heat evolved divided by the specific heat times our delta T. So we'll write this out. So 619.74 times 10 to the 6 joules. Divide that by our specific heat, so 4.186 joules per gram degree Celsius, and times that by 51.2 degrees Celsius. So when we calculate this out, our mass of water is going to be 2.89 times 10 to the 6 grams. Alright, so to find the volume of our water, we know that volume is equal to mass over density. So we know that the density is equal to 1 gram per 1 milliliter for water. So our volume is going to equal our mass, so 2.89 times 10 to the 6 grams, times that by milliliter per 1 gram. And then we want this in liters, so 1 liter for every 1,000 milliliters. So when we calculate this out, our volume is equal to 2,890 liters of water that can be heated. Alright, and that is how we solve the last part of this problem.